2016 Mazda 3 has a lateral acceleration of 0.81 Gs. How fast can this car take the city corner without a radius, with a radius of 20 meters without sliding? All right, so the lateral acceleration is the sideways acceleration. So for circular motion, the lateral acceleration is the centripetal acceleration, and that's going to be 0.81 Gs for this problem. So if I'm looking at this, let's start by listing our givens. All right, I know that the lateral acceleration, which is the centripetal acceleration, is 0.81 Gs. Now I can't use 0.81 Gs in any math we do, so I got to convert this over to meters per second squared. So I'm going to say that AC is equal to 0.81 times 9.8 meters per second squared. That's going to give me a number that I can use in all my calculations. So that's 7.938 meters per second squared. And then it wants to know about this radius. So the radius is going to be 20 meters. All right, and the question I'm asked is how fast can it go around? So I want the tangential velocity because it's going around a circle. So how fast can it go around the circle? All right, so for part A, what I'm going to do, let's see, I've got AC, I've got R, I've got V. So looking through my circular motion relationships, I'm going to use the fact that AC is equal to the tangential, it's supposed to be a V, tangential velocity squared divided by R. So that means looking for the velocity, so the tangential velocity is equal to the square root of AC times R. So the tangential velocity is equal to centripetal acceleration, 7.938 meters per second squared. Remember, you can't use G's, got to use our SI units. And the radius was 20 meters. All that's under the square root. So the tangential velocity in this case is going to end up being, quick little calculation here, 12.6 meters per second. So a little more than 25 miles per hour, 12.6 meters per second. That's how fast. That would be the maximum it could go under ideal circumstances. That's, nice, clear, dry road, nothing on the road, perfect situation. Like that's going to happen. Okay, part B. Part B, a circular ramp with a radius of 80 meters is used to exit the highway. So let's look at my givens for part B. That's going to be, R is equal to 80 meters. And the speed limit is 20.12 meters per second. Can this same car travel around at 90 miles per hour? That's twice the speed limit. All right, so there are a couple things to look at here. Let's see, there's my velocity, and there are a couple ways to figure this out. Velocity is 40.24 meters per second. I'm not going to use the 20.12 at all. So what I need to do, one of the ways I can do this is I can compare like supply and demand. The car can supply 0.81 Gs of lateral acceleration or centripetal acceleration, and the demand would be the curve. So what is demanded by the curve at 40.24 meters per second with a radius of 80 meters? So anything, as long as my supply can meet the demand, I can go around the curve. So for example, if I do the calculations and I get a centripetal acceleration of 0.5 and my car can do 0.8, then I can supply 0.5. That's easy. But if I do the calculations and it comes out to be 0.9 and my car says 0.8, then I can't do it. The car cannot supply what the curve demands. So let's figure this out. So AC, I'm going to use the same equation as I did before, VT squared over R. So AC is equal to 40.24 meters per second squared divided by 80 meters. So AC is equal to, whoa, that's a big number, 20.24 meters per second. So in terms of G's, if I divide this number by 9.8, then erase that a little bit. What that's going to do, meters per second squared. When I do the calculations, that's going to be AC is equal to 2.07 G's. So that's what the curve is going to demand to make it at that speed. The curve says you got to be able to supply 2.07 Gs because that's what I demand with this velocity and this radius. And this car does 0.81. There's no way it's going to make it around this curve, so it's not going to make it around the curve. When it hits it, it's just basically going to slide straight off the curve. I don't think there's a car on the market except for on the market that's 2.07. Maybe some Formula One race cars could do that, but not your street cars. So if your demand is bigger than your supply, you can't do it. If your demand for the curve is lower than your supply, you can make it around the corner. Now, just to be clear, in the real world, it's not this simple. The tracks aren't comparable. Usually the curves are cement. They have little pebbly pieces of, looks like little marbly pieces of rubber on the road. They also have fluids dripped off from the car, so they're slick. So this 0.81 is under ideal dry conditions on the perfect track. In the real world and on the roads, the calculations just aren't quite this easy. They don't work out.